All right. Hello, everybody. We are almost done with content, just 2 more lessons. So in today's lesson, what we're going to learn about is the final mechanism that you need to be aware of. And then afterwards, we're going to go over colors and being able to tell color differences in reactions, like how to tell apart whether you have an aldehyde, a ketone, and other different functional groups. So lo and behold, let's go ahead and get started. First learning objective, and this is traditionally it would have been 2 class periods, one for the mechanism and one for the other part, but I am combining it since we are meeting every other day. Objectives. Learning objective 18.1b. Describe the mechanism of the nucleophilic addition reactions of hydrogen cyanide with aldehydes and ketones. So nucleophilic addition. Addition means that I'm going to be adding 2 components, an X and a Y. In this case, 2 aldehydes and ketones. And a nucleophilic addition means that you are going to be adding a nucleophile. So this is an interesting reaction, to say the least. You'll be adding the nucleophile in first, and this is one of the, I think it's 5 mechanisms altogether that we need to be aware of, and it's the final one. So notice you're adding 2 components, which you would do in a standard addition reaction. In a standard addition reaction that we learned about in organic part 1, you would add across the double bond. And so, for example, if you had H and OH, which was water, to add, you'd add 1 part to the carbon on the left, and you'd add 1 part to the carbon on the right, and you would follow Markovnikov's rule to put the hydrogens where there's more hydrogens, and the other group where the carbon has more carbon surrounding it. In this case, though, you would actually be adding the 2 groups, again, across a double bond, but that double bond will be the double bond of the carbonyl group. So C double bond O, by the way, I might have said this in another lesson, but I'm going to say it again. It is called a carbonyl group when you see it, and when you see COOO, that is actually called a carboxyl group. So it's slightly different, carbonyl versus carboxyl. So a carbonyl group is exclusively used for aldehydes and ketones. We call them carbonyl groups. And if it's a hydrogen on the end, it's an aldehyde. And if it is a carbonyl group in the middle of a chain of carbons, it's called a ketone. And so we'll be adding across the double bond. What exactly? It says hydrogen cyanide, so HCN. And I think you might have an idea of how this goes if you think about it, if you're savvy. If you think about it, if I want to add HCN, and these are the 2 components, and I know that CN would be the negative part and hydrogen would be the positive part, it should make sense that the cyanide would connect with the carbon and the hydrogen would connect with the oxygen when it's added across. And so that is one part because positives are attracted to negatives and negatives are attracted to positives. And this would be partially positive and partially negative due to electronegativity. All right, so let's go ahead and get started. First with the bell work. When heated, KOH is dissolved in ethanol, halogen alkanes undergo elimination reactions to form alkenes. What are the possible elimination products when 2-bromobutane is heated with KOH dissolved in ethanol? So let's take a look. 2-bromobutane, CH3, CH, CH2, CH3 with bromine on the second carbon, which I like to expand out the functional group. And so you really do have 2 options here, possible elimination products. And they're not even giving you the cis-trans options. You've got an option to put the double bond this direction. You will have CH2, CH, CH2, CH3. And you've got the opportunity to put the double bond in the other direction between carbons 2 and carbons 3. So you could have CH3, CH, CH, CH3. And so that gives you, proper answer would be C, because these are the possible elimination products. And in this choice, they didn't even give you that third option of having the cis variant versus the trans variant. So let's take a look at the addition reaction. We're adding across the C double bond O bond, like I'd said earlier, and the idea is simply the following. You think of the hydrogen cyanide, and this can also work with sodium cyanide, or any cyanide. That's two components, in the following way. The carbon is partially positive and the oxygen is partially negative. So remember that negatives repel with other negatives, and that positives attract to negatives. So if you understand it that way, just think about this. Take away the double bond, add the hydrogen. The hydrogen adds to the side with the oxygen because hydrogen itself would be positive, and the oxygen would be negative, partially positive. And the cyanide would be negative, and this carbon is positive. So the cyanide would add in here. And so you'll notice that your product would be the cyanide added where the carbon is, and the hydrogen added where the oxygen is. And that is the simple reaction. So every time I have an aldehyde or a ketone, I can add hydrogen cyanide to it, and I will end up with what's called a hydroxypropane nitrile. And you are responsible for knowing this reaction. Once you have come up with your cyanide product, you can do two things with it that you do need to be aware of. Your cyanide can be turned into a carboxylic acid, or your cyanide can be reduced into an amine. Let's take a look at how that can happen. If I want to turn my cyanide into a carboxylic acid, I use a strong acid to do so. And so I would end up with a carboxylic acid. Because you see a line here, this means the rest of. So just any compound. And then if I want to reduce the nitrile to an amine, I'm going to use sodium actually and ethanol to do so. And you would end up with CH2NH2 for that to occur. All right, so let's take a look over the mechanism really quick. Hold on. Okay, so this mechanism, as drawn out, just be careful with your curly arrows. The 2 electrons here would go to the carbon, not to the bond. And then this bond curves over immediately to become 2 electrons on the oxygen. And so those are the 2 extra electrons that are being shown. Once you have that happen, then this negative will reach out to the hydrogen that's still around from hydrogen cyanide, and you will end up with the alcohol. So you end up actually with 2 functional groups. You end up with the cyanide attached, and you end up with an alcohol. Let's take a look at another. So I'm going to go ahead and just write a random reaction. This is a ketone and HCN. So the way that this works, and for sake of space, I'm going to write the arrow down, is you always go from negative to positive with your curly arrows. So if you have H plus and you have Cn minus, recognize that those 2 electrons, and you don't have to write the H plus next door, because if it's an acid, the H plus can be broken off, so you can write the cyanide by itself. You could also write, if you did write it like this, you could Just recognize if you do so, you have to show this happening to give the 2 electrons to the carbon, and then you would have to show these 2 electrons. So this is where you begin. Go and grab this carbon. And at that point, the carbon will have 5 bonds, which is not okay. So the second bond for oxygen moves up, and you end up with the following as your intermediate. Your 2 new electrons plus all the valence electrons that oxygen had. It's now fully negative because you've added an electron. You've got your CN that you've just attached. You've got CH2, CH3, and then you've got H plus all alone by itself. And so then all that happens is these 2 electrons come in, grab this hydrogen, and you end up with your final product. CH3, CH2, C, CH2, CH3, OH, CN. All right, so then in the checkup, it says name the organic product that would be formed in the nucleophilic addition of HCN to ethanol. Remember that when you name it, you name the alcohol as in substituent. So when alcohol is a substituent, it is called hydroxy. So the first one would be, I'm just going to draw the reaction first. Ethanol is CH3, COH. I know I'm adding a CN and an H, so it would be CH3, CH, OH, and CN. They didn't ask me for the mechanism, they just asked me actually to name what the product was. So this would be 1, 2, 3, but really going this way because the side with your functional group will be the end. And so this would be 2-hydroxy propane nitrile. Because when naming cyanide, you name it a nitrile group, and how you name nitriles is you count the carbons and you just say the whole entire name of the carbon chain and add nitrile to the end. All right, propanone. So let's try it again. You just add the OH and the CN, where you have this right here. And so the name of this would be, again, it's propane nitrile, because it's 3 carbons in a row. And it's 2-hydroxy because of this, but it's also 2-methyl. So it's 2-hydroxy, 2-methyl, propane nitrile. All right, so that's really it for the first part, which is the mechanism part. The second part is testing for aldehydes and ketones. So if you just have a random clear liquid in front of you and it's some kind of organic molecule, how do we know if it's an aldehyde or a ketone? How do you tell the difference between them? And honestly, like, how do you know if it's an aldehyde, a ketone, an alcohol, a carboxylic acid? What are some ways that we could tell the differences physically with chemical tests? like by observing color, by looking at boiling point and other physical and chemical properties. And so that's what we're going to be looking at here. So there are 2 more objectives to go over. Learning objective 18.1c is to describe the use of 2,4-DNPH, 2,4-dinitrophenylhydrazine reagent that's a mouthful, to detect the presence of carbonyl compounds. And learning objective 18.1d is to deduce the nature, aldehyde or ketone, of unknown carbonyl compounds from the results of simple tests. Fellings and Tellins reagents, and then ease of oxidation. So simple chemical tests are adding specific reagents and looking at the color change that occurs. So let's take a look at the bell work real quick. It's a carboxylic acid, and they ask you what starting materials could you use to synthesize propanoic acid. So go ahead, take a little while, see if you can get the answer, and then we will review it. Okay, so can alcohols become carboxylic acids? Sure. Can cyanide become carboxylic acid? Well, if you paid attention, I said it probably about 10-15 minutes ago. Sure. With an acid, you can hydrolyze cyanide in acid and water to become a carboxylic acid. And finally, can aldehydes become carboxylic acid? Sure. The answer here is all 3 statements are correct. All right, so let's take a look. Testing for aldehydes and ketones. And I did leave this from the lessons from before because you are still going to take mock exams. And there generally tends to be a lot of questions that involve this specific type of material. Being able to identify what type of compound you have based on the chemical and physical properties seems to make sense that there would be a decent amount of questions. So this is very similar to qualitative analysis, but I am asking you to go ahead and know these color changes based on the different functional groups. And so we can determine, so let's say we have an amine, we have a carboxylic acid, we have an ester, we have an aldehyde, and we have a ketone. And we're trying to figure out, there's 5 different test tubes and 5 different functional groups in those test tubes, and we want to know what is in each one, which type of functional group. So there are ways you could find out, but one of the ways to find out if that functional group out of all of these functional groups is an aldehyde or a ketone is to pour a small amount, a couple of drops of a solution of this large molecule, 2,4-DNPH. So it's made in a lab and it is used for this specific chemical test, and you put it into the test tube, and if you either have an aldehyde or a ketone, it will do the same thing. It will turn it'll turn bright orange, so from a colorless to bright orange, and so you'll see a rich precipitate for 2,4-DNPH. However, with an amine, a carboxylic acid, and an ester, the liquid would remain clear. So it only tells me, hey, I have an aldehyde or a ketone. So just thinking, like, how would I know if I have an amine? How would I know if I have a carboxylic acid? How would I know if I have an ester? What are some other ways of being able to determine? Well, it turns out that a lot of times it's not perfect, but you can use your sense of smell to help you to determine if there is a specific type of molecule, because amines, for example, they smell like fish. And so if you have a fishy smell, that's amine. Amine is a derivative of ammonia, NH3, which has a really strong, really not a lovely smell. For esters, they usually are fragrant, meaning that esters are what gives flowers their nice smell. So esters usually they're used in fragrances. So people will develop fragrances out of flowers, and it's because of those esters why they smell pretty nice. And so then a carboxylic acid, they don't really have a smell, but because they're an acid, they'll do any acid-base reaction. So we could determine we have an acid, we can have a carboxylic acid by putting an indicator in and seeing if we see a color change, by reacting with a base and seeing, for example, if I have Na2CO3, it would actually fizz because it would make water and carbon dioxide, so I'd get the fizz effect from it. And so there are different ways to tell that you have different functional groups. And if you do take organic chemistry in university, you would do these tests. You would do these type of tests for the different organic groups. You could also determine if you have patience and you have time, or your professor forces you to, you can find the melting points of the different groups that you have. For example, if you have solids of different aldehydes and ketones, they're not dissolved in solution, you can determine the melting points or the boiling points, and the melting point is usually what we use. And different functional groups tend to have different types of boiling points because of their different intermolecular forces. All right, so let's take a look at a Cambridge question. Which reagent gives the same visible result with propanal and propan2-ol? See if you think you have the answer, and then I will go over it. All right, so let's see if you got it. So 2,4-DMPH would do the same thing for aldehydes and ketones. So the answer for this is not 2,4-DMPH. So if you answered it simply because that's literally the last thing we went over, whoopsie. The next one, let's look at this. Cr2O7. Cr2O7 will oxidize an aldehyde to a carboxylic acid, and it will oxidize a secondary alcohol to a ketone. So in both scenarios, it would turn from orange or yellow to green, and therefore will give the same result. So your answer is acidified potassium dichromate. Sodium reacts with alcohol, but not with propanol. And Talon's reagent is something you'll see in a little while. All right, so you took a look at, do I have an aldehyde or a ketone? Like, now, how do I tell if it's an aldehyde or a ketone? So if we want to tell if we specifically have an aldehyde or if we specifically have a ketone, we could either determine the melting point, as I mentioned earlier, and then you could look at reference values to determine what you have. As long as your unknown compound is pure, this would work. You could also do other chemical tests. So let's say you have, this is going back to 2,4-DNPH. Let's say you have an aldehyde. Aldehyde itself is clear liquid. What you can do, and you have it in a test tube. You can add AgNO3 and ammonia. Sounds familiar. If what you have is an aldehyde, you will go from a colorless solution to a beautiful silver mirror. If we were in class, we would have actually done this. I had gotten the materials for it, unfortunately. we won't be able to unless we come back before the end of the school year. But this would be the result. You'd get a beautiful silver mirror, which you could then keep. So if I have an aldehyde, I'll get a silver mirror. If I have any other functional group, it won't give me a silver mirror. So once I've determined I've added the 2,4-DNPH, and I saw that I got this color, orange precipitate, I would take my samples, I would prepare 2 new test tubes that have my potential aldehyde and ketone, and then I would add Tollen's reagent being AgNO3 with NH3. If I get a silver mirror, then I will have an aldehyde, and if I have something that turns that orange color because of the reaction with 2,4-DNPH, but then when I add into a separate test tube Tollen's reagent, I would see that it does nothing, meaning that it stays colorless. There is a second reagent that you can use to test that almost does the exact same thing, except the color result is different. And this is called Felling's solution. And so this is a solution of copper sulfate. So actually, if you add copper sulfate to an aldehyde, the color of the copper sulfate will turn to orange. So if I have a blue to orange test result, this is using Felling's reagent, and this is a positive test for an aldehyde. So it's a positive test for an aldehyde. So then, old Cambridge question. Which of these compounds can be oxidized by acidified dichromate and also gives a positive response to Tollen's reagent? See if you can figure it out. Okay, so acidified dichromate is for alcohols, aldehydes, and we'll turn them and oxidize those. Also gives a positive response to Tollen's reagent, means that what you have has to be either, well, actually it can only be one thing. It has to be an aldehyde, because Tollen's reagent will only oxidize aldehydes. So then, which of these scenarios do you have aldehydes? I see an aldehyde, CHO in X, and I see an aldehyde in Z. So it would be X and Z only. And the next question says, which reagent will give similar results with both butanone and butanal? So I'm looking for the functional group. Ketone, aldehyde. Which of these gave the same result for both ketones and aldehyde? Well, that was at the beginning, 2,4-DNPH will do that. It gives you that orange precipitate. And the final question, aldehydes and ketones are carbonyl compounds. Which of them react with NABH4 and with Felling's reagent? So NABH4 will reduce both aldehydes and ketones. Felling's reagent only reacts with, and here it is again, aldehydes. So it goes back to forever ketone. Because most of these reagents, if you'll notice, only react with aldehydes and not the ketones. Forever ketone. But both of them would react with NABH4. So which of them will react with NABH4 and react with Felling's? That would be aldehydes only. This is a review flowchart, and you can develop one of your own. but it gives you an idea of how to analyze the questions. Do I have a carbonyl group, which means C double bond O? Yes, then add 2,4-DNPH. If I see a orange precipitate, it means a carbonyl group is present. If there is no PPT, then it means not aldehyde or ketone, and you would have to do something else. Well, if I get the orange precipitate into a new test tube of whatever it is, I would, in order to find out if it's an aldehyde or a ketone, I would either do Tollin's test or Felling's test. You don't need to do both, just one or the other. So you add silver nitrate and NH3. If you get a silver mirror, it's aldehyde. If you don't, ketone. The end. Same thing with Felling's. If I see a reddish brown precipitate, it's an aldehyde. If it stays the copper sulfate blue color, then it's a ketone, as long as you get that orange precipitate. So then checkup 5, melting points of the derivatives are shown. So taking a look at the different melting points, it doesn't help you with this question. The question is, what would be observed when each of the carbonyl compounds is mixed with 2,4-DNPH? Did you get it? Orange precipitate. Because that happens with both the aldehydes and the ketones. So what would I add to an unknown compound to see if it contains a carbonyl group? Once again, 2,4-DNPH. What would I get if the unknown compound does not contain a carbonyl group? Colorless solution. And why would it be useful to find the melting point of the product of this test? You could determine whether you had an aldehyde or ketone based on known melting point values, as long as what you made is pure. Before we close out, just one more thing. I do want to say that although I didn't really include it in this lesson, I want to bring up, because there will be questions about it in chemical tests. The chemical test for carboxylic acid is, or one of them is Na2CO3. The reason why is with carboxylic acids, you would end up with that replacement reaction where you would end up with CuNa and you would end up with H2CO3. Well, H2CO3 is one of those things you have to remember breaks up to become water and carbon dioxide. And so it fizzes. So your chemical test for a carboxylic acid is if you throw sodium carbonate into it, it'll actually work with any carbonate. It'll work with calcium carbonate, whatever. But if you throw a carbonate, it'll start to fizz. And other functional groups don't do that because other functional groups are not acidic in nature. So that's how you can identify if you have a carboxylic acid. So I want you to also make sure you have that in your notes, because you can be asked how to identify carboxylic acids along with identifying aldehydes and ketones. All right, we're almost done. We have just a couple more topics that we'll discuss in the last part of chapter 18. So have a great day, and see you for the next problem-solving session.